Hello guys, you want to start lecture 41. So in this lecture, I want to talk about non-homogeneous boundary value problem and about their solution. So first of all, we have to know what non-homogeneous boundary value problem is. I already explained in the past lectures. A boundary value problem is said to be non-homogeneous if either the partial differential equation or boundary conditions are non-homogeneous. For example, here you can see we have one partial differential equation, k second derivative of u with respect to x plus f of x and t is equal to derivative of u with respect to t. Here you can see that we have f of x and t. That's why this partial differential equation is non-homogeneous. If you look at the boundary conditions, so you can see we have u of 0 and t is equal to u0, u of 1 and t is equal to u1. The boundary conditions are also non-homogeneous, and we have initial condition which is u of x and 0 is equal to gx. So in fact here we have one non-homogeneous heat equation, and in these problems, in non-homogeneous boundary value problems, maybe separation of variables is not applicable. So in this lecture you want to see how we can solve these type of problems. In order to solve these type of problems, we have two solutions, two techniques. In this lecture, I talk about the first one, and in the next lecture, I'm going to talk about the second technique. So in the first solution or first technique, this solution is applicable when partial differential equation and the boundary conditions are time independent. For example, see here we have partial differential equation k second derivative of u with respect to x plus f of x equal to derivative of u with respect to t. In fact, this term fx that makes partial differential equation non-homogeneous, it's time independent. Also, if you look at the boundary conditions, so we have u of 0 and t is equal to u0, which is a constant, and u1, it's another constant, so u0 and u1 are time independent. As a result, this boundary value problem is time independent, and we can use the first solution. So let's see how the first solution is. In this solution, we have to assume that u of x and t, so which is a solution of non-homogeneous problem, it's equal to summation of v of x and t plus psi x. In fact, instead of finding u of x and t, at first we find v of x and t, then we find psi x, then we add them together, so we can find u of x and t, or solution of non-homogeneous boundary value problem. If we assume u is equal to v plus psi, now I find second derivative of u with respect to x and derivative of u with respect to t and plug it in the partial differential equation. So second derivative of u with respect to x, it's equal to second derivative of v with respect to x plus second derivative of psi with respect to x, which is psi double prime x. And if you want to find derivative of u with respect to t, it's equal to derivative of v with respect to t plus derivative of psi x with respect to t. Psi x is not function of time. As a result, derivative of psi with respect to t is equal to 0. So it means that the derivative of u with respect to t is equal to derivative of v with respect to t. Now I plug it in the equation, in the partial differential equation. So we have k times second derivative of u with respect to x, and we have second derivative of u with respect to x is equal to second derivative of v with respect to x plus k psi double prime x plus fx, it's equal to derivative of u with respect to t, which is equal to derivative of v with respect to t. We could find a new partial differential equation, and we have to find v and psi x. In order, this equation still is non-homogeneous. In order to make this equation homogeneous, so I assume that, in fact, I find psi x such that k times psi double prime x plus fx is equal to 0. Why I do that? Because if k psi double prime x plus fx is equal to 0, so what is left in the equation? So we have k times second derivative of v with respect to x plus, so we have k psi double prime plus fx is equal to 0. So it's gonna be equal to derivative of v with respect to t. As a result, I could make one homogeneous partial differential equation. Now we have to go through the boundary conditions. So we have u of 0 and t, it's equal to u0. So u of 0 and t, it's equal to v of 0 and t plus psi 0, and it's equal to u0. I assume v of x 0 and t is equal to 0, and psi 0 is equal to u0. Why I make this assumption? Because I want to make one homogeneous boundary condition. So in fact, now I have v of 0 and t is equal to 0. And here we have psi at 0 is equal to u0. For a second boundary condition, so we have u of 1 and t is equal to u1, and it's equal to v of 1 and t plus psi at 1. Again, I assume that v of 1 and t is equal to 0. Why? Because I want to make homogeneous boundary condition, and I assume that psi 1 is equal to u1. So again, here we have v of 1 and t is equal to 0, and here we have psi at 1, it's equal to u1. And the last initial condition, so we have to find v of x and 0. V of x and 0 is equal to u of x and 0 minus psi x. So you can see we could end up with one ordinary differential equation with two boundary conditions and with homogeneous boundary value problem, and we know solution of this homogeneous boundary value problem. If I can find psi x such that k psi double prime x plus fx is equal to 0, and psi 0 is equal to u0, and psi 1 is equal to u1, then I can easily find v as well. Then I add them together, and it results u of x and t, which is solution of our problem. Now we have to solve one example to see how we can find psi x. But the only thing that I have to explain is about this initial condition, how we ended up this initial condition. So you know that we know that u of x and 0, so it's given in the problem, so it's equal to gx. And we assume u of x and 0 is summation of v of x and 0 plus psi x. As a result, v of x and 0 is equal to u of x and 0 minus psi x, that we can see here. and it's equal to gx minus psi x. So now we solve these two equations and we can end up with the solution of our problem. Let's solve one example to see how it works. We want to solve this boundary value problem. K times second derivative of u with respect to x plus r is equal to derivative of u with respect to t. R is constant. So you can see partial differential equation is non-homogeneous. Why? Because we have r in the equation. As a result, we have non-homogeneous boundary value problem. But you know this, it's time independent because r is constant. And if you look at boundary conditions, so u of 0 and t is equal to 0, u of 1 and t is equal to u1. u1 is the constant, so it's time independent as well. As a result, we can use first solution to solve this boundary value problem. So based on the solution that we had, we said we have to assume that u of x and t is equal to v of x and t plus psi x. Then we have to find second derivative of u with respect to x. Second derivative of u with respect to x is equal to second derivative of v with respect to x plus psi double prime x. Derivative of u with respect to t is equal to derivative of v with respect to t, and derivative of psi with respect to t is equal to 0. I plug it in the partial differential equation. So we have k second derivative of v with respect to x plus k psi double prime x plus r is equal to derivative of u with respect to t. Derivative of v with respect to t is equal to derivative of v with respect to t. So it's equal to derivative of v with respect to t. So we have to get rid of this term. As a result, I find psi x such that k psi double prime x plus r would be equal to 0. We have two boundary conditions, so u of 0 and t is equal to 0. As a result, v of 0 and t plus psi 0 is equal to 0. So I assume v of 0 and t is equal to 0, and psi 0 is equal to 0 as well. So here we have psi 0, it's equal to 0. And for boundary value problem, so when k psi double prime plus r is equal to 0, so what is left? So we have k times second derivative of v with respect to x is equal to derivative of v with respect to t. And the first boundary condition is v of 0 and t is equal to 0. Let's go through the second boundary condition. So the second boundary condition says that u of 1 and t is equal to u1. So it's equal to v of 1 and t plus psi 1. So it's equal to u1. I assume that v of 1 and t is equal to 0. Why? Because I want to make homogeneous boundary condition. So we have v of 1 and t is equal to 0. And we have psi 1 is equal to u1. So psi 1, psi at 1, it's equal to u1. So now we have one ordinary differential equation. We have one homogeneous boundary value problem. So we have to find initial condition as well. We have to find v of x and 0. So if you look at here, we have u of x and 0 is equal to x. U of x and 0 is equal to v of x and 0 plus psi x. So it's equal to x. As a result, v of x and 0 it's equal to x minus psi x. So I say v of x and 0 is equal to x minus psi x. We have this ordinary differential equation, so let's solve it to find psi x. So k psi double prime plus r is equal to 0. As a result, psi double prime x is equal to minus r divided by k. So it means that psi prime x it's equal to minus r divided by k. X plus c1, c1 is the constant, and psi x is equal to minus r divided by 2k x squared plus c1x plus c2. Now we have to find c1 and c2. In order to find c1 and c2, we have two boundary conditions. We know that psi at 0 is equal to 0. As a result, c2 is equal to 0. We have psi at 1, it's equal to u1. So it means that minus r divided by 2k times 1 plus c1, it's equal to u1. As a result, c1 is equal to u1 plus r divided by 2k. So we could find c1 and c2. It means psi x is equal to minus r divided by 2k x squared plus c1. So c1 is u1 plus r divided by 2k times x. Now we have psi x. Now we have to find v of x and t. So v of x and t, we have one boundary value problem. You can see it here. I just write it down here again. First, we have to see what v initial condition is. So the initial condition, we had v of x and 0 is equal to x minus psi x. So it's equal to x minus psi x is r divided by 2k over x squared. So we have minus here is going to be plus minus u1 plus r divided by 2k times x. It's v of x and 0. So I just rewrite this boundary value problem. So we have k second derivative of v with respect to x. It's equal to derivative of v with respect to t. Boundary conditions, we have v of 0 and t is equal to 0. V of 1 and t is equal to 0. And the initial condition, we have v of x and 0. It's equal to x plus r divided by 2k x squared minus u1 plus r divided by 2k times x. So you can easily solve this homogeneous heat equation. We already solved it. That's why I just write the final answer. So we have, if you solve it, you're going to see v of x and t is equal to summation of n from 1 to infinity an e to the power of minus k pi squared n squared times t times sine n pi x. And if you want to find an, so an is equal to 2 times integral from 0 to 1 integral of x plus r divided by 2k x squared minus u1 plus r divided by 2k times x dx. So you can easily find this integral. So you have a n, you plug it in the series, you have v of x and t. V of x and t is known. Psi x, we already found it here. We have minus r divided by 2k times x squared plus u1 plus r over 2k times x. We have both v of x and t, we have and psi x. As a result, we could find u of x and t, which is solution of this non-homogeneous boundary value problem. So conclusion, because we had one non-homogeneous boundary value problem, but it was time independent, we could use first solution. We assume that u is equal to v plus psi, and we just plug it in the equation. We found psi, we found v through a homogeneous boundary value problems, and then we add them together to find u of x and